All right, today we're going to talk about one of the most elegant and, honestly, powerful ideas in all of computer science: consistent hashing. This is one of those brilliant, kind of hidden architectures that lets the biggest services on the internet scale up without completely falling apart. So let's dive in.
I mean, really think about it for a second. You've got these massive services with millions, sometimes billions of users. They're adding new servers all the time to keep up. So how do they pull that off so smoothly without everything just crashing? Well, the secret is in how they solve a really tricky data distribution problem, and that's exactly what we're going to unpack here.
So before we can really appreciate just how clever the solution is, we have to get our heads around the problem. And it turns out that the first, most obvious way to distribute data across servers, well, it leads to an absolute nightmare when you try to scale. Just imagine this. You've got a perfectly happy system running on 4 servers. Everything's humming along nicely. But you're growing, so you need to add one more server to handle the new traffic. You'd think, hey, more power, great. But nope. With the simple approach, this one tiny change can trigger a total, catastrophic failure of the whole system. And what's wild is how simple and logical the flawed approach seems. You take a piece of data, like a photo's file name, you hash it to get a big number, and then you use the modulo operator. Hash %n, where n is your number of servers. It's basically just the remainder from a division problem, which gives you a number between 0 and 3 if you have 4 servers. Seems like a perfectly reasonable way to assign data to a server, right? Okay, and this is where it all falls apart. The moment you add that 5th server, your n changes from 4 to 5. And because that divisor in your little math problem changed, the answer changes for almost every single key. I mean, look at that. We're talking about 80% of your data is now, according to the formula, in the wrong place. The consequences are just disastrous. This huge data reshuffle is like causing a gridlock traffic jam on every single road in your system, all at once. All your caches are now wrong, the network gets totally flooded with data being moved around, you get what engineers call a network storm, and the whole system can just grind to a halt. We absolutely need a better way. So that's the nightmare. Now, let's talk about the elegant solution. And this isn't just a little fix, it's a completely different way of looking at the entire problem. So here's the big aha moment. The hash function itself, it's perfectly fine. The real villain, the little piece of math causing all this chaos, is the modulo operator. It's the thing that ties every key's location directly to the total number of servers, and that's what makes the system so fragile. And that realization leads to this just beautiful shift in perspective. You have to stop thinking about your servers as being in a straight line, an array from 0 to n-1, and you have to start thinking in a circle. And this is it. This is the hash ring. It's an abstract idea, kind of like a clock face. And on this clock face, we're going to place both our servers and our data keys. This one simple change in how we visualize the space is what's going to solve that whole scaling nightmare.
So, how does this ring actually work its magic? Let's walk through the mechanics, because it's actually pretty cool. It's a really simple 3-step dance. First, you take each of your servers and you hash its name or IP address to find its spot on the ring. Then, you do the exact same thing for your data key. Hash it and place it on the ring. So where does the data go? Easy. You just start at the key's position and walk clockwise until you bump into the first server. That's its home. That's it.
All right, now for the moment of truth. Let's add our new server, server D. Look what happens. It gets placed on the ring, and the only data that has to move is the stuff that was living on server C, but now falls before server D. All the other keys on the ring, they don't even know anything changed. They stay exactly where they are. We've contained the blast radius. And this is the payoff, right? In tech speak, we call this all of k/n. But what that really means is that the number of keys you have to move is just a small fraction of the total. Basically, the total keys divided by the number of servers. Instead of moving 80% of everything, you're only moving a tiny, manageable slice. This right here is what makes horizontal scaling possible. Okay, so the core idea is brilliant. But, the real world is always a little messier. So a couple of really important refinements were added to make this work in production systems. So what's the first problem you'd run into? Well, what if you just get unlucky with your hashing? You could end up with all your servers clumped together on one side of the ring, and now you've got one server responsible for a huge arc of the circle, while another one is barely doing any work.
That creates a hotspot, and that server is going to get totally overwhelmed. The solution is, well, it's really clever. It's called virtual nodes, or vNodes for short. The idea is, instead of putting server A on the ring just once, you pretend it's, say, 100 or even 1,000 little mini servers, server A1, server A2, and so on. And you place each of those virtual nodes on the ring individually. What this does is amazing. It's like, instead of throwing one dart at a dartboard and hoping you hit a good spot, you get to throw hundreds of darts. The law of averages kicks in, and your physical server's presence gets spread out all over the ring much more evenly. The load balances out beautifully, and the whole system becomes way more stable and efficient. Okay, last piece of the puzzle. What happens if a server just dies? Because servers fail all the time. To solve this, we layer on replication. When a key is assigned to its main server, say server B, the system also copies that data to the next couple of servers it finds clockwise on the ring. So now, if server B goes offline, no big deal. The data is still safe on server C and server A, and the system just keeps right on chugging. So let's pull all of this together. Why is this one concept so incredibly important for the way the internet works today? Well, consistent hashing, especially when you add in virtual nodes and replication, is the engine that truly enables massive scalability and fault tolerance. And this isn't just theory. It's the core architecture inside some of the biggest databases on the planet, like Amazon DynamoDB and Cassandra. It's the concept that powers distributed caches like Memcached, huge load balancers, and data platforms like Kafka. It is everywhere. So if you had to boil it all down for, say, a job interview, here's the perfect soundbite. Consistent hashing maps servers and keys onto a circular space. That minimizes data movement when the number of servers changes. And you use virtual nodes to make sure the load is spread out evenly. That's the whole thing in a nutshell. Consistent hashing is just this beautiful example of an incredibly elegant solution to a really complex problem, and it's working invisibly behind the scenes all the time. And it really makes you wonder, right? What other brilliant hidden architectures are out there, quietly holding our digital world together every single day?